Alright, good morning. So here is our third out of 4 lessons on circuits, and we're going to be talking about parallel circuits. Okay, so last day what did we talk about? We talked about series circuits, and what's that? That's when you have a battery and it goes around and it connects to a lamp and then another lamp, something like that, where it has to go through one to get to the other. So that's a series circuit. So now we're moving into something called parallel, where essentially it doesn't have to go through one to get to another. It can branch off. It could either go through that one, or it can go through this one, or it can go through this one. Okay, so parallel is just where it branches off, and the current doesn't have to go through all of the resistors. It can choose one of them to go through and then make it back to the battery. Okay, so that's what a parallel circuit is. So circuits which branch off into different resistors. All right. So this next question says, draw a series circuit, so one from last day, with 2 light bulbs of resistance of 6 ohms each. Okay, so I kind of did that there, but we'll do it again. 1, 2, and I'll put the 6 ohms, and we'll come from a 120 volt outlet. Okay, so there we go. There's a series circuit. Now it says do the same thing but make it parallel. So how you do this is generally what I like to do. This picture is a bit misleading because it shows kind of a pathway in between 2 and 3 and 3 and 4. But generally parallel branch off all from the same point. So I like to draw it 1 back to the battery, and then I'll draw another one branching from the same point and returning there. So I have my 2 light bulbs there. So that's a parallel circuit. If there was another light bulb, I would branch off from the same point and come out here and then return back to the same point. That's why this is a bit misleading, those types of pictures, but they still represent the same thing. Okay, so here's 2 light bulbs, 6 ohms, 6 ohms, and our voltage is 120 volts, still going around, still going around. So the interesting thing here is with series, if you remember, it would go around, voltage would drop, and then the rest of the voltage would drop, and it would return to the battery with 0 voltage. So here, since they are the same resistor, you would bet that that one would be 60 volts and that one would be 60 volts. They'd share the voltage because their resistance is the same from the battery. So in this question, though, it's not the same thing. They go around 120 volts, and what happens to the voltage is you can see that the current can choose to go left or right, and then something happens where a certain amount drops and then we return back to the battery. My guess would be it would still return to the battery with 0, so it has to distribute the volts in there. You could guess that maybe it's 60 volts and 60 volts again, but let's see what happens. Okay, from last day, what is our equivalent resistance of our series? That one up there. Well, if we remember, equivalent resistance just means the overall resistance of the whole circuit, not just the light bulb, which is 6, but what's the resistance of the whole circuit? Well, we use Req is R1 plus R2, and in our case it was just 6, and another 6. So that series circuit has an equivalent resistance of 12 ohms. So overall, this whole circuit has 12 ohms of resistance from the battery, or to get from one end through everything back to the battery. It goes through 12 ohms of resistance. Now it says, what is our equivalent resistance of this parallel circuit? Okay, and we actually don't know that. We haven't gone through it. So I have a little circuit here that I can show you. I got this time 2 batteries, give it a little more juice. They're 1.5 volts each, but if you put one against the other like this, you actually add the voltage together, so it'll be roughly 3 volts, probably a little bit less. I
I took a reading and it said 2.6 volts. Okay, so almost 3 volts when I put them together. And then I have two light bulbs here. You can see it, one's not really connected there, but this one here is connected into the series. So as soon as I touch these circuits together, you can see it lights up. And it's a lot stronger than last day because I have two batteries. But it's going to go through the circuit, through this battery, and back to the other battery. You can see that this one here, it's not lighting up. It's because it's not in a closed circuit. The current is not going to go through there because it just ends off and doesn't return. So I'm going to make a parallel circuit by touching this to the alligator clip, because then it has a choice to go through this light bulb or this light bulb, and then branch off there and then return to the circuit. Okay, so essentially I'm making a parallel circuit here with just one cord, and then they branch off and they'll get to choose which one they want to go to. Okay, so if it's like a series circuit, if I add another light bulb, there's going to be a voltage drop through both of them. And essentially if I connect this, then it should dim this one, right? Because then we have twice as many resistors, and so it should drop some of it there and drop some of it there. So let's see what happens. I touch it. Do you see the other one lose any light? Not really. So you can see when I touch it, it adds a current through both of them. Okay, and it doesn't really look like it lowers the light heat at all, right? So something different is happening. It's not the same rule as before. So I wonder what the overall resistance is. So I took a reading before, and I found out when you're doing just one like this, the current running through the system is 0.14 amps, 0.14 amps. But then when I touch it with this second one, the amps increases to 0.26 amps. Okay, so it nearly doubles the amount of current that's going through, but you can see the voltage seems to stay the same. So my thoughts here is that when you connect things in parallel like this, you're actually taking more juice from the battery because the voltage seems to stay the same, but current increases. Okay, so if voltage stays the same and current increases, that means your power has to increase as well. Okay, so the power output from the battery must increase with parallel circuits. But now let's just do another test here just because I'm interested. I'm going to disconnect one of them, and I'm going to connect one like so, and you can see same amount of voltage is happening, is dropping through this. Pretty much all the voltage of both the batteries are being dropped just through here because there's minimal resistance in the wires. So I'm going to connect one here, and I'm going to make a series circuit just by touching them like so, because it has to go through this one to go through the other one. And if we look, when I touch them, they're a lot dimmer, you can notice, right? A lot dimmer going through both of them. And that's because half of the voltage drops there and half of the voltage drops there. Okay, so they're really only taking half the voltage, and if we test the amount of current that's going through them, let's test. See if I can show you this. I have those zeros is my ammeter, and I'm going to connect both sides. You can see the light bulbs light up because I made a circuit, and it tells me how many amps are running through. 0.11. So it's half the amount of amps running through. Same amount of voltage, but half the amount of amps. So you can see that series circuits take less power, but essentially make your light or show less power, that is. Okay. All right, so that's that circuit. So what did I just show there? Just showed that parallel circuits are different than series circuits. So our equivalent resistance, you're gonna bet, is not quite 12 ohms of resistance. So what is it? Let's look at that.
We have equivalent resistance. This should be Req down here for equivalent resistance, or the resistance of the whole circuit. For a parallel circuit, say like this one, with 3 resistors, is 1 over the equivalent resistance is equal to 1 over R1, 1 over R2, and 1 over R3, and however many there are. That's why it goes dot, dot, dot. So it says, or here, I find a more useful equation than this one, is what is Req? Well, to solve for Req, you put 1 over on both sides. And essentially, Req is going to be equal to 1 over R1 plus 1 over R2 plus 1 over R3 dot, dot, dot. So it's the same thing. You just put 1 over this side here. Okay, so this one is the one that I'm going to use. I'm not going to use that one. This one is a lot more useful. 1 over R1 plus 1 over R2 plus 1 over R3. All right, so that actually happens to be the Req of parallel circuits, surprisingly. So the interesting thing that happens with the equivalent resistance, if you looked at series circuits, it went 6 plus 6, 12 ohms. So your equivalent resistance increased in a series circuit. So the resistance was more in the circuit. But if you look at the parallel circuit here, it's 6 and 6. But if I use this equation here, it would be 1 over 6 plus 1 over 6, or using my calculator, I'll show you how I calculate it. I go 1 over 6 plus 1 over 6, just do the bottom part, and then I go 1 divided by second answer. And I get 3. Okay, you could type the whole thing in at once, but it's a little more tricky. 3 ohms. Okay, so if you notice, your equivalent resistance is less than the resistance of the lowest resistor. Okay, so usually you get smaller resistance amounts when you increase the amount of pathways, essentially. So another way I could have wrote this in is 1 divided by bracket, 1 divided by 6 plus 1 divided by 6 bracket. All right, so this here is another important part. The statement here I would really remember. In series, our current stayed the same and voltage dropped for every resistor. So in this example here, your current does not change throughout. It's the same current, it's just your voltage or your pressure drops, and your voltage or your pressure drops again. Okay, it's kind of like water running downhill. Your pressure dropped, but the speed that it fell down still continued to be the same. Here, in parallel, our current out equals our current in, so the amount of current that goes in the battery must be out must be the amount of current going in, and our voltage stays the same. Okay, but if it branches off, you can actually decrease currents. So here you have a certain current, here it must be the same entering, but when you go through here, some gets dropped there, some gets dropped there, or essentially the current splits and there's less current in each of these 3 than comes out. But when you hit this branch point again, they all add up again, and then the current is the same as the current that went in. Okay, and that's the little simple equation. The amount of current going in is equal to the amount of current going out if you added it up. Okay, so let's try this question here. A 60 volt battery, which is a really large battery, car battery is only 12 volts, is connected to 4 loads, 3 ohm, 5 ohm, 12 ohm, and 15 ohm in parallel. And then it has some questions on it, but let's just draw the picture first. So we got 60, and I'm going to show that it branches off into 4. So there's my 4, and then it comes back to the battery. Okay, so parallel with 4 things. So I'm going to call this 1, and it's going to be 3 ohm. 2, it's going to be 5 ohm. 3, it's going to be 12 ohm. And 4, it's going to be 15 ohm. So we have this, and then the battery they're saying is 60 volts. And it says find the equivalent resistance of the 4 loads together, or the whole circuit. Okay, since it's parallel, you know it's going to be less than 3 because that's the lowest one. If it was series, you know it would be just them all added up together, but it's not. It's parallel, so let's go Req is equal to 1 over 1 over 3 plus 1 over 5 plus 1 over 12 plus 1 over 15. And that gives us an Req value of, you got to use your calculator, so I'm going to 1 divided by bracket 1 divided by 3 plus 1 divided by 5 plus 1 divided by 12 plus 1 divided by 15, close the bracket, 1.46 ohms is my Req. Okay, so if I look, that is less than the smallest one. So it's interesting how the resistance decreases so much with parallel circuits. Okay, and what happens when it decreases, if you use Ohm's law, you'll notice that the current that has to leave the battery must be more than if this R value decreases. Okay, so this is one. Number 2, find the total current leaving the battery. Well, it's V equals IR is our normal equation, but it's leaving the battery, so that R must be Req. So if we want I, it's going to be V over Req. Our voltage from the battery is 60 volts. And my Req is 1.46. So overall it's 60 divided by 1.46, which is 41.09, or just 41.1 amps coming out of that battery. That would be a lot of amps, and it would heat up very quickly. I guess this is one thing to note: when you put too many parallel circuits together, you're going to increase the heat of whatever the whole circuit is by a lot. So 3, find the current through the 12 ohm load. So it just wants to know the current that's going through here. Because if you know parallel circuits, a certain amount of current is coming out, 41.1 amps, but when it hits this branching off point, some of it's going to go there, some of it there, some of it there, some of it there. Okay? Generally more current goes with the least, so that one's going to have the most current, and then less, and then less, and then the least amount of current going through this one, because that one has the most resistance. Okay, but how much current is coming through this one? Well, we can calculate it using just V equals IR. Not Req, but just R. So here, it's 3. The interesting thing with parallel circuits is looking at this part. In parallel, our current equals, and our voltage stays the same. So this voltage, the 60 voltage, stays the same for all of them. So all these light bulbs have 60 volts of pressure in them. Okay, so with parallel, they all stay the same voltage, doesn't change. So our voltage in our third one is equal to our current in our third one times the resistance of our third one. So if you want to know the current going through the third one, it's V3 over R3, which is going to be 60 volts, since it's parallel, divided by 12 ohms for that one, not Req, but the 12 ohm one. And they go 60 divided by 12, and we get 5 amps of current running through that resistor. Okay, so from 5 amps out of this 41.1 amps is being currented through that resistor there. Okay, and you could do it with all the other ones if you wanted, but it only asks for that one. All right, so 4 practice questions. Good luck. Please ask if you have any questions.